All right, so number one says find the value of the absolute extrema for the function on the interval from -1 to 3, state theorem and conditions. So this is extreme value theorem. So extreme value theorem, the whole point is to find the absolute max, absolute min. There's only one condition involved with extreme value theorem. Function is continuous with brackets from A to B. And then our steps is, we know we're going to test endpoints, so we're going to save that for later. We have to find critical points. So critical points comes from your derivative. Um, find critical points. This is where you're setting f prime of x equal to 0. And remember, if you set f prime equal to 0, if there's a numerator and denominator, you got to consider both numerator and denominator. And then make sure that whatever critical points you find are inside the interval if we want to involve them. And then we'll test them in addition to endpoints back into the original function, and then compare your y values. Highest y value is your absolute max. Lowest is your absolute min. All right, so go ahead and try number one, and I'll work through it at the same time that you guys try it. My key has the x value as part of the solution, but you can ignore it. Just give me the y value for your max and min. Okay, any issues with critical points? Are both these valid? -4/3 is what? It's outside the interval. So that's like -1.3 or something, that's going to be further left than our left bound. So we can ignore that -4/3, but 0 is safely inside the interval. So we're going to test 3 candidates. Right? They go all back into the original function. Don't give me order pair. Don't give me the x value. I just need the y values. Any questions with extreme value theorem? Yeah. Yes, I will. Yeah, I want the emphasis on the y value. You could say absolute max is 45 at x equals 3. That indicates to me that you still know that 45 is emphasis here, but I would just say just ignore the x values just so that one less thing to worry about. Just give me the y values. Yeah, no order pairs. Right. Number 2 and 3 involves Rolle's theorem and mean value theorem. Let me go through just reminding us of that process. So really, it's really mean value theorem. Rolle's theorem is just a subset of it. So mean value theorem, the whole purpose is we're trying to find a place on the curve where the slope matches the slope of the average rate of change. So there are 2 conditions involved with mean value theorem and Rolle. Function is continuous, bracket, differentiable with parentheses. You really, for us, for now, you only have to worry about continuous. If you can just make sure that there are no discontinuities that's impacting the interval, and if you can get past that condition, then the second condition will follow along with it. Okay, make sure we state it. The formula is basically within this setup here. This is telling us to find the order pairs and find the slope between the 2 endpoints. So no calculus to begin with. You're just doing change in y over change in x, and then finding that slope. This slope for mean value theorem can be -5, it could be 0, it could be 8, it could be 3. And then once we find that slope, then we turn around and we find the derivative, and we set them equal to each other, and we solve for x. Our x is our quote-unquote c value, and where does the c value have to live once we solve for x? Yeah, inside the interval. So it has to be between the interval. If it's at the endpoint, we have to remove it. But you're guaranteed at least one to be sitting inside between the interval. If there's more than one inside the interval, then you can keep both as your solution. But you're guaranteed at least one. And endpoint is outside the interval. Now, Rolle's theorem is basically the same thing as mean value theorem. It's just that when you find your order pair and you find your slope, slope has to end up being what? And what's the easy way to tell that the slope is going to be 0? If your order pair has the same what? Same y value. If you have the same y value, you're going to get, 8 minus 8 or, 5 minus 5. You're always going to get a 0 in the numerator if you get that same y value. So that's the only distinction between mean value theorem and Rolle's theorem. If this doesn't end up giving you a slope 0 or a value of 0, then it breaks down. It doesn't quite work for Rolle's theorem. Rolle's theorem wouldn't apply because the slope here doesn't equal to 0. The mean value theorem can be any slope. 0 could be a positive number, it could be a negative number. Okay. Any questions? What's the process? Okay, all right, so try 2, and then I'll work through it at the same time that you guys try it.
Y values were different, we would use mean value too?
No, it's asking specifically for Rolle's theorem, so it will just break down and it'll say it doesn't apply. So yeah. You're right. I mean, if it was anything other than 0, technically it can work from mean value.
Wait, so couldn't you just know that you're both gonna get 2 5s from -1 and 5?
Yeah.
So when you, okay.
Yeah. So I'm just showing this to indicate that it's the same process as mean value theorem. But yeah, if you saw that, this is going to work. then jump directly into saying that equals 0. You don't have to show all this additional stuff. I just want to make it where it's just an offshoot of mean value theorem. I don't want us to feel like it's a drastically different process. Yeah, if you see that connection, you can jump directly into setting these equal to 0. Okay, so 0 over 6 is 0. That's a real number. So we can move forward. So now we're just asking, we know the curve is going to have to experience a slope 0. So we're asking the derivative to tell us the location of that slope 0. So that 0 will go in for f prime. And we're just solving for x. We're guaranteed at least one solution inside the interval, and we're getting that guarantee there. Try number 3. Same condition, same formula. It's just that this doesn't have to be a slope 0. Okay, try those steps. But it's virtually the same process as number 2. Another polynomial, easy to identify and write out our conditions. Find your endpoints, find your order pairs, find your slope. Slope doesn't have to be 0, as long as it's a real number. We're able to move forward. Average rate of change of 4. So we know that somewhere along this graph, there's a guaranteed place where this curve is going to experience a slope 4, and we're basically looking for it. So make sure the 4 goes in for the slope variable, and we're simply looking for the x value. Are both of these valid? Just what? Just -1, yeah. One is right at the endpoint. You're guaranteed at least one in between. Now, if you don't find any in between, then something went wrong. We're guaranteed at least one solution between the interval. We shouldn't have a no solution once we get past the first two conditions. Right, so I'm not exactly sure. So there must be a condition somewhere that that mean value theorem is not able to guarantee this location. And I think the reason why is because it's only guaranteed to be differential between -2 and 1. And so because of this condition that we can only, that if there's a sharp turn at the endpoints, we don't care about it. And so because it's not quite inside the interval with it being a smooth curve, that means that whatever our C value is, it has to be in a place where we have a protected smooth curve, and it's not inside this condition. And so that's why one is outside that interval.
Okay, so kind of.
Yeah, exactly. Yeah, this is overriding the bracket there, right? Okay, any questions with critical points, extreme value theorem, Rolle's theorem, or value theorem? Right. I think this is the more challenging portion of the content-wise in terms of the theorems and recognizing the steps. I think the second page will feel easier because I think we're more familiar with first derivative test for concavity. Okay, so any questions with page one? Okay, let's go to page 2. Okay, so number 4, f of x is a polynomial given. Find the following interval where the function is increasing, decreasing, relative max, relative min. And this is all going to be within first derivative test. So you're going to find f prime, set f prime to go to 0, find your critical points, create your f prime sign line, and then everything that you need will just be pulled from your f prime sign line. Now, I am asking for maximum, relative maximum points. So that means when you find, after you find your x value, you still need to find what? Y value. And how do you find the y values? Back into division, okay. And then justify your answer. So you're going to have to practice writing out all your because statements. So because statements for increase, there's because statement for decrease, there's because statement for relative max, because statement for relative min. Okay, so work through that, and I'll do the work as well as you guys try it. So we're gonna have two intervals of increase, one interval for decrease. Remember, your test points are not gonna be involved in your statements. Okay, on my key, I didn't indicate the Y values, but let's see if we can find those Y values using our calculator.
Nifty increasing from -10 to -2. Big flip flop.
Sorry about that. Yeah, we change that. Oh. Wait.
That's to be lawful.
Increasing is greater than 0. Fix. So what you guys got?
The Y value.
No, I'll say, yeah, 2 or 3. I'm not gonna be specific here. Any variation is fine if I ask you for it.
Okay,
Yeah.
and it would just be the order pair.
If I ask you for the point, yeah, it's the order pair. If I just say, give me the X value of the relative max, then yeah, your instructions will indicate what I'm looking for.
Is it?
Right, only for extreme value theorem, we don't want the X values at the end, just the Y values, right? Right, any questions with first order test? All right, number 5, this is a test for concavity. Hopefully this won't take the entire space. I want to have space for 5B, where we can practice a second derivative test for number 4. So with test for concavity, you're working your way down to F double prime, and then you're going to be doing a lot of the same things that you did with the F prime sign line, but not at second derivative level. And then the plus at the second derivative level is not going to be representing concave up. Negative is not going to be representing concave down. And then your critical points, if there's a change in sign, you call that a point of inflection. So number 5, we have to make our way down to the second derivative function, f double prime, set that equal to 0, solve for x, we get 0 and 2. I'm using test points to determine whether each interval is positive or negative, but now a positive is going to represent concave up, negative will represent concave down. And I'm just writing out each of the statements purely from my sign line. My points of inflection, the y values come from the original function. So go and go back into the original function, get those y values. Our reasoning is because f double prime changes signs. We don't have to specify the order of sign change. As long as you specify that there's a sign change, that's good enough. And make sure that when you write your because statement, that you don't just say, because sign changes from positive to negative. You have to specify what function you're referring to. F prime is what's changing here. Here is f double prime that's changing. So make sure that that you're naming, that you say graph, you don't say it, you don't say signs. Those are not clear enough. Make sure you specify the function you're referring to. Okay, are we okay with 5? Okay, 5b is applying second derivative test. Let me remind us this process for a second derivative test. Second derivative test also finds relative max, relative min. So if we're going back to number 4, we'll get the same result, but different process. So here's the process. You're going to still set f prime equal to 0. You're still going to find your critical points, but the difference is you're not going to create a sign line. You're going to take those candidates from f prime and stick them into the f double prime function, and then you're looking at your second derivative value. The numeric value it's kind of abstract. We don't really care about the numeric value. We just care about, is it a positive or is it a negative? If you get a positive second derivative, that means the graph is concave up. If the graph is concave up, the shape will be a U shape, and the only place with where the slope is 0 is going to be a place where there's going to be a relative minimum. And then if you get a negative number, that means that your graph is part of concave down. If it's part of concave down, you're staring at a relative max. So we're going to attempt number 4, finding, we already know the max and mins. There's going to be a max at -2 and a min at positive 1/4, but we're going to go through a different process and see if we can get the same result, but going down a different path. All right, so let's try 5b, which is the same function as number 4. We're getting the same conclusion as number 4, but just going down a different path. No sign line, and we're just relying on these numeric values to help us confirm whether we're staring at a concave up graph or concave down graph. If it's concave up, we know we must be looking at a relative minimum. If it's concave down, we know we must be staring at a relative max. The place where that students get tripped up is we associate positive with something higher. So a lot of students want to say relative max because of that positive 9. Some students want to say a relative minimum because of negative 9, but we know that these numbers are not locations. These are curvature values. We want to be able to word them as concave up, concave down. And if we can see the shape of concave up, concave down, we should be able to convince ourselves whether it's relative max, relative min. But it's the same result as number 4, right? We got the same conclusion, relative max at -2, relative min at 1/4. But just going down a bit. All right, number 6. Any questions so far? Okay, sketch the graph, labeled graph of the function with the following characteristics. So we have a bunch of order pairs here. We can plot them when we're ready. The hope is that if we can create a slope and concavity sign line based off of these notations, then we can use the sign lines to kind of give us a picture of the graph. So can we word this a different way here? Let's start with the second statement. F prime is less than 0 for x is less than 2 or x is greater than 4. How would you phrase this? F prime less than 0 means what? Yep, negative slope where? Left of 2 and to the right of 4. So using that, we can create a sign line with a visual component, right? So any x values they provide for you are going to be critical points. So we know negative slope to the left of 2 and to the right of 4. Okay with that. F prime of 2 does not exist. There's a number of ways to represent this, but what does this mean? F prime of 2 means what? What's another word for F prime? Yeah, so slope does not exist. Now, this can either mean there's a sharp turn, or if you want, you could also treat this like, oh, the point doesn't even exist, right? The slope doesn't exist because the point doesn't exist. So I would say sharp turn, but if you want to say a vertical asymptote or hole, those are also potential possibilities, but you can choose whichever one that you want to create out of that information. Well, actually, we know it can't be a vertical asymptote or hole. Why is that? Yeah, because so this one, it does define that point. So we do know that if the point's defined, then we can eliminate these options. Okay. All right, f prime of 4 equal to 0. What does this mean? Yeah, slope is 0. So at x equals 4, slope is equal to 0. Okay. We know that it's going to be a flat point, either a hill or valley, or the graph is going to be leveling off at a moment at that point. Okay, f prime of x is greater than 0, or x is between 2 and 4. What does this mean? Positive slope. Yeah, so we can finish our slope sign line with that second to last statement. All right, final statement. F double prime is less than 0 for x doesn't equal to 2. How would you say this? Everywhere except 2. They do indicate 2, even though it doesn't say equal to 2. If they indicate any x value, it's going to be an indication that's going to be a critical point. So at the f double prime sign line, we can create 2 as our critical point. So we know on both sides, which is make both concave. Yeah. So the way I like to graph this, I like to create 2 versions. One version is mapping out the path of the graph. And then the second version is retracing that path with the appropriate curvature. But I like to start off with order pairs. Order pairs kind of gives you some anchor points across your graph. So I'm not going to look at my curvature graph. I'm just going to look at my slope. I just want my graph to match that slope behavior. So my graph is going to be decreasing up until I hit 2. It's going to increase until I hit 4. And it's going to decrease after that. So when you go through and retrace with your curvature, you're not going to create a new path. You're just going to kind of move along this path that's already been set. So make sure that you don't create a new path out of this. So I want my graph to be decreasing, but the entire time it'll be remaining concave down. But what do we know about 2? There's something here. Sharp turn, right? So we're going to make it a sharp turn here. Concave down, sharp turn. Concave up, concave down. And it's going to remain concave down. But I know there's going to be slope 0 here, so it'll be a relative max. I will say that some students may want to do this. They see, okay, this is concave down, so why not do a whole full concave down, right? Then I can get that full concave down shape. What's the issue there? It needs to be what? Decreasing, right? So once we map out that decreasing path, we're not going to get away from it. So we're going to move along that path. So you're only going to show a concave down within the restriction that we've already established. Still going to be increasing, but it's never going to quite have the full curvature that we would associate with the full concave down. Okay, how do we feel about these problems? Your quiz is not until Wednesday, but I wanted to make sure that we're comfortable with it so that you guys can kind of be on your own as you prepare for a quiz. There's one more thing that is not on here involving critical points. So why don't we use the bottom half of it says page 32. It says optimization notes. The optimization won't be on it. This won't take the whole page. So if you can just go to the very bottom here, and we'll just do a critical point problem, finding critical points problem here on page 32. Find one for us. Okay, find critical points. X to the 8/5 plus x to the 3/5. So the whole process here is you're going to find f prime, but you're going to end up with two separate fractions that we have to involve common denominators to merge them into the same fraction. And once you get your f prime down to one fraction, you can set the numerator equal to 0, denominator equal to 0, and those are your critical points. So, okay. let's try that process. Notice that your f prime is separate fractions. In order to find critical points, we have to get this down to one fraction. So we do need common denominators. So what's going to be a good common denominator for both these fractions? Yeah, 5 is 2/5, right? This is large enough I can handle this 5 as well. So establish those common denominators, and then we have to figure out how to balance each fraction. So this old denominator also different from this new denominator. You multiply the top by x to the 2/5, right? If I multiply variables, what I do with the exponents? Add them. 2/5 plus 3/5 is 1. So I'm just left with 8x. Any adjustments here? No. So numerator will just be what? Yeah. So now that I have common denominators, I can cleanly get them into the same fraction. And once they're under the same fraction, then I can set both top and bottom equal to 0, and then I can find my critical points. And then I'm done. So as you guys prepare for your quiz, I would go back to your quiz review packet and practice those problems. I think there may be a worksheet here that you may not have done. I think page 13. So if you haven't done that, you can try that for additional practice. I'm available tomorrow morning for a help session. And then also Wednesday morning, I'll do a morning review, picking out one of the worksheets or going through additional problems. But your quiz will be this. It'll be like 10 problems, just very similar to the process that we did. Okay. Tomorrow we'll cover optimization. Optimization will not be on your quiz. We're just trying to get ahead and making sure that we can get ready for our test review when we start test review on Thursday.
And when they live there, but like, you know, like sneak people in, stuff hard to do there. They're all, yeah, but like, they just put them on under Smith, and it's like 5 sandwiches in Smith. And 2 of them are friends with them, so it's like not much good. And they're playing golf, and you play broken, right? No. The lanes are really tight, like extremely. I think I've been to, I haven't really been. Well, like, hole 1 and 3 are ideally tight. And like we were like, a little bit, and that part